Hello, friends. So let us begin with the new topic of climatology, which is very important and holds an important place in the syllabus of NET JRF examination. The topic is air pressure and winds. So first today we will deal with what is air pressure. So once we look at the elements of weather, the most important of them are air pressure and winds. Now, air pressure is an important constituent of weather, and it is associated with other elements in a cause and effect relationship. So we understand this that the uh, cause for pressure is the amount of air at a particular location, then the temperature of that area, okay, and then the winds are a direct result of the air pressure. The variation in the air pressure from place to place, it is responsible for the movement of winds. And we all know that if the winds were not there, then the transport of heat and moisture would not have been possible. Air pressure is a very important phenomenon when we are dealing with the weather forecasting. So you must have seen in the weather news that the air pressure variation maps are shown. Okay. Now, the regional variations in the air pressure, they are produced by temperature. So the area which has high temperature has low pressure, and which has low temperature has high pressure. This is universal truth, and we will see its application and how this is done in the subsequent slides. But other than the temperature, there are several prevailing wind systems which are also caused by the dynamic factor of the rotation of Earth. So, as we do the wind movement, we will also see that what are the factors that are responsible for the movement of winds and all. Now, how do we define air pressure? So, like everything on this planet, air also has some weight. Okay. Now, the as we all know that in physics the pressure is defined as force per unit area, okay, and what is force? Force is simply the mass in is a product of mass and acceleration. So once we are dealing with, let us say that this is a column of air, then the mass of this air, if it is m, so the force applied by this air will be Fg, that is force equal to gravity. So the Fg will be m into the acceleration due to gravity, that is g. Okay. And if let us say that this is the surface of 1 meter square, so the Fg which is being applied over this area will be the pressure. So pressure is equal to force applied upon area. So if let us assume that uh, the mass of the column over a particular location is 10 kilograms, and the area over which we have to find it out is 1 meter square, then the force 10 multiplied by 10 upon, so approximately 10, because g is equal to 9.8 meter per second square, so it will be into 1 meter square. So this will be 100 Newton per meter square. So this will be the pressure which is applied by the this column of air over this area, which is 1 meter square. Now, if we see here in this particular diagram, we can see that the molecules which contribute to this weight of the air, they are variable at various altitudes. So if we see here, at the lower heights, the height which is closer to the Earth's surface, we can see here that the air is denser because a lot of molecules are closer to each other. As we go up in the altitude, the air becomes rarer. So we can understand this, that as you go up the altitude, up the height, the air pressure decreases. So it is closer to the sea level, and as you go above the sea level, the higher you go, the air pressure becomes lesser. So the air pressure is therefore defined as a force exerted against a surface by a continuous collision of gas molecules. Because all these molecules, they are not stable, they are in motion, so they collide with each other. So they apply force. Okay. So the amount of pressure exerted uh, at a particular point is determined by two factors. They are temperature and density. So we can understand this, that the pressure, the air pressure, is directly proportional to temperature and density. So if we go by the gas law, then pressure is equal to constant multiplied by temperature multiplied by density. So imagine, let me add a screen over here. Let me add a slide over here, not a screen. Imagine we have two locations on the earth, location A, location B. The pressure at A is equal to the pressure at B, but the temperature at location A is less than temperature at location B. Okay, so what I'm trying to say is that we have two locations A and B which have same air pressure but different temperatures. Location A is cold, location B is warmer. So what about then the column of height of the column of air pressure? So at location A, where the temperature is less, it means that the height of air column will be a smaller one. So let us say HA. But at location B, where the temperature is more, it means that the height of this air column will be more because of that equation rho T into constant. So if the temperature of a location is lower, it means that the density of the air at that place should be higher. Always remember this, that if there are two places which have same air pressure, one of the places is colder than the other one, then the density of the air at the cooler place will be lesser than the density of the air at the other place. Means the air column has to be higher at location B, because the pressure over here is a product of density and temperature. The atmosphere, it exerts a pressure of 1034 grams per square centimeter. Now, there are various types of units and values given. So, the atmospheric pressure. So, first of all, what is atmospheric pressure? It is the pressure force being applied by the atmosphere per unit area. So, even we, as we are standing on the earth, we have the entire pressure of the atmosphere on our shoulders, on our head. So how do we counter this atmospheric pressure? The blood pressure. the blood pressure of a human body is same as that of the atmospheric pressure. That is why we are able to withhold the atmospheric pressure. You must have seen that as people go on mountains, higher heights, they suffer the problem of bleeding from ears and from nose, because then at the mountains, at the higher heights, the atmospheric pressure becomes less and blood pressure it exceeds. As a result, the arteries they burst. That is why few people have this problem of bleeding nose and bleeding ears. The instrument used to measure the atmospheric pressure, it is called as barometer. First barometer was developed by Torricelli. He was a scientist on, and on his in his honor, another unit of uh, pressure is torr. So let us have a look at different units of measurement of atmospheric pressure and what are the various values which you should remember, because sometimes in the section B they may directly ask you this. So the SI unit is Pascal. We all should remember this, that this atmospheric pressure, which is also known as barometric pressure, its SI unit is Pascal. In normal terms, you must have come across several times in different physics and chemistry textbooks that the pressure is given in atmosphere. So 1 atmosphere. Now 1 atmosphere, in if it is written in SI units, it can be written as so 1 atmosphere, it is equal to, so all these values they are 1 atmosphere, equivalent of 1 atmosphere. So 1 atmosphere is equal to 1.01325 into 10 to power 5 pascals, or 101.325 kilopascal. Now in mmHg, it is 760 mmHg. 760 mmHg can also be written as, so Hg is mercury, 760 millimeter mercury is also written as 76 centimeter Hg. Okay, or 760 torr, or 1.01325 bar, or 1013.25 millibar, or 14.7 psi. So psi is pounds per square inch. It is FPS unit. So SI unit is Pascal, and the unit which is commonly written in everyday language is atmosphere. The standard sea level pressure is 1013.25 millibar. You should remember that the pressure is never static. It always keeps on changing. It varies from day to day. That is, we have the diurnal variations in the pressure, we have the seasonal variations in the pressure, and we have the annual variation in the pressure. And you should also remember that the highest sea level pressure on the earth occurs in Siberia, where the Siberian high often attains a sea level pressure of 1050 millibar, okay, or 105 kilopascal. This is the average, and sometimes it goes as high as 1085 millibar. So you can imagine that the values of pressure they keep on changing, and therefore the wind velocity is never static. Wind velocity can also change as per the changing pressure. Okay. Now, it is very commonly seen that the places which have high pressure, they are associated with clear skies. So remember that high pressure is associated with clear skies and stable weather, while low pressure systems they produce cloudy weather. Why does this happen? So if you see over here, as the air starts to sink, okay, in the upper atmosphere, the air which is, it is sinking. As this air sinks, so now we know that at height the air molecules are far away from each other. They are rarefied. As they start to sink, their volume decreases. They come close by. As they start coming closer, and furthermore they become more close. They become quite compact. Now the work is being done to bring all the molecules together. As a result, this is called as the adiabatic heating. Adiabatic heating. Now, the air which is close to the surface of the earth at the now as this air starts coming in, all the molecules become they become compact. They will exert more pressure. As a result, the earth encounters high pressure with sinking air. Now, as this air becomes warmer, as it comes closer to the earth's surface, it has the ability to block all the moisture close to the earth's surface. So as the air starts to become warmer, it will absorb all the moisture and it will not let it go up. As a result, there will be no cloud formation and the weather will be clear. But in case of rising air, now here, as this air it starts to rise up, during the rising of the air, the closer molecules of air, they start to go far from each other. They become rarefied. Now, as this uh, air as it goes up, it starts to you know uh, expand. Now, the moisture which is here at the Earth's surface, it is now released. As it is released, the heat of condensation allows these water vapor to form clouds, to fall as precipitation, and therefore the weather it does not remain clear. Now, you should understand this, that once the air is sinking, it is coming closer to the earth, the work done to heat that air, it does not allow the earth's moisture to go up in the atmosphere. No cloud, no precipitation, clear weather. So on in the winter season, normally we see very clear noon skies, while during the summer season, we normally, as this air goes up, we see a lot of cloudiness, hazy weather. Okay, so you should know this fact that the high pressure is associated with clear skies and stable weather, while low pressure systems they produce cloudy weather. Next topic is the pressure gradient. So basically, the pressure gradient is defined as the decrease of air pressure between 2 points along a line perpendicular to the isobars divided by the distance between the 2 points. So these are all isobars. So how do we define isobars? Like isotherms, isobars are imaginary lines which join the points having similar pressure on the Earth's surface. So in this case, in this diagram, you can see two uh, isobars, one of 1000 millibar, the other one of 995 millibar. So if we have to find out the pressure gradient, so we understand this that isobar of 1000 is at a higher pressure than isobar of 995. So this isobar is of uh, low pressure. So in this case, the air will start to move from high pressure to low pressure like this. Okay, because the try to understand it this way. If we have two air columns, here the amount of air is more, and here the amount of air is less. So definitely the one which is having more will give it to the one which is having less. As simple as that. So how do we calculate the pressure gradient? Let us say that the center of these two isobars, it is 100 kilometers apart, and the difference here is 5 millibar. Okay, so if we see this, it is, so the pressure gradient is equal to 1000 millibar minus 995 millibar divided by 100 kilometers. So it is 5 millibar per 100 kilometers, or we can write it as 0.05 millibar per kilometer. This is the change in uh, pressure. Now you have to understand, just like temperature, that when over a long distance, when over, listen to this very carefully, when over a long distance, the difference in temperature is very high, then we call that gradient as a steep gradient. And when the difference of temperature is less over a long distance, it is called as shallow temperature gradient. Similarly, when the if you see in this, the upper one, the difference in the pressure from 1020 to 1012, so 8 millibar over a long distance. So here the pressure gradient is shallow, means that when over a long distance the difference between high pressure and low pressure is not much, it is called as shallow pressure gradient, and therefore the wind speed will be lesser over here. But if we have this difference as quite high, so in this case we have 16 millibar over a same distance. So here the pressure gradient will be steep and wind speed will be high. This pressure gradient is a very important property which helps in the generation of winds, and of course it controls the weather systems. Now, let us look at the types of pressure variations. Normally, the pressure variations are of two types. The diurnal variations means the change in the pressure every day. So it is daily change. The other one is seasonal variation. Now, diurnal variation is very important. Here, it is because of the insulational heating and radiational cooling. Now, let us say that if this is the Earth's surface, this is the sun, the insolation being received by the sun on the earth, it heats up the earth, and the radiation, the terrestrial radiation, it cools the earth. So this insulational heating and this radiational cooling, they will impact the temperature of the air. As a result, the pressure will be varying. And if you remember my class on the temperature distribution, we had seen that the temperature of the atmosphere is not highest at 12 noon, rather, it is much later in the afternoon. So, we receive two maxima and two minima in 24 hours, and therefore it is also referred to as semi-diurnal maxima and minima. So, you should remember this, that of course there are variations, no doubt, but on an average, the pressure is maximum two times a day at 10 a.m. So 10 hours. So this time the 10 hours or 10 a.m. and 10 p.m. While it is minimum at 4 a.m. and 4 p.m. uh, this ideal condition of variation in the diurnal pressure at 10 a.m. and 10 p.m. and 4 a.m. and 4 p.m. it occurs normally at equinoxes, but every day the maxima and minima are observed closer to these values. So in the morning at 4 o'clock and evening 4 o'clock we get the minimum pressure, while in the morning 10 o'clock and later in the night at 10 p.m. we get the maximum pressures. Now, this this diurnal variation is due to the phenomenon called as atmospheric tides. These atmospheric tides are very similar like the ocean tides, and this atmospheric tide or solar tides, as they travel through the atmosphere, they keep on changing the pressure of the air. The magnitude of this change in the pressure, it decreases from equator towards the pole. So as we go from the equator to the through the tropics to the poles, the change in this air pressure is very little perceivable. Means you are not going to perceive much of this change at the poles because of the less variation in the insulational heating and radiational cooling. While at the equator and the tropics, it is quite perceivable because of the significant change in the temperature due to insulational heating and radiational cooling. So that is the diurnal variation. And the seasonal or annual variation. So as we know that the earth goes around the sun and that is causing the sun to distribute its insolation in different fashion. So we have solstices, we have the equinoxes, we have the perihelion and aphelion positions. So the effect of annual variation in the amount of insolation received in a particular region is the one of the major causes for seasonal or annual variation of pressure. Annual pressure variation in tropical regions is larger than in the other regions of the world. Why does this happen? This happens because if you remember, we had seen that during the solstices, it is the tropical latitudes which receives maximum insolation rather than the equatorial latitudes. So once the amount of insolation is highest at the tropics, it means that the pressure variations will be more in the tropics, and as a result, the tropical latitudes, they are the house for maximum disturbed weather, the unstable weather, while equatorial region, they have the smallest variation in their seasonal pressure because the amount of change in insolation, the annual change in insolation, is not much. Now, the third last point in this is the over continents. High pressures are recorded during cold seasons, while over oceans they are recorded during the warm season. So it is exactly reverse. If you remember, the continents, the land masses, they had the highest temperatures during the warm season, while the oceans, they had the highest temperatures during the cold season. So high temperature is always associated with the low pressure. Now let us have a look at this important fact, that if we have the cold season, then according to this statement, during the cold season, the pressures on the land mass are the highest. Therefore, we have these, and the oceans, they are the lowest, they are the lower, relatively lower than the land mass. So you must be aware of the fact that during the cold season, during the winter season, the winds, they blow from the land towards the ocean. So if you let me give you the example of monsoon. So the northeast monsoon, it goes from land towards the sea. But during the warm season, what happens? During the warm seasons, the oceans, they are cooler, therefore they develop high pressure, while the lands, they develop the low pressure. And as the wind blows from high pressure to low pressure, we get the reverse pattern of the monsoonal wind. So they are the southwest monsoon. Now, the reversal of these winds is just because of the changing pressure conditions on the landmass as well as the oceans. Uh, the variation in the air pressure is also the reason for the development of cyclones. Let me add a slide over here. Now, I'm just introducing this topic of cyclone here to arouse your interest. We will discuss cyclones in details once we do the chapter on frontogenesis, cyclones, and anticyclones. Now, what happens over here? What is a cyclone and what is an anticyclone? So, if you read the definition of cyclone and anticyclone, cyclone is the circular motion of the winds with low pressure at the center, which is also called as the eye of the cyclone, while anticyclones, they are circular motion which have the high pressure at the center. So, the low pressure at the center means that it will be having higher temperature. So, any area which has higher temperature, it normally gets the low pressure. So, in case of a cyclone, if we have the low pressure over here, so what it will do, it will cause the convergence of air mass towards the center. So all the air will start coming in from high pressure towards the lower pressure center. While in case of anticyclone, there is high pressure at the center, so it will cause the movement of air outside. Now, many of you must have read this, that the cyclones, in the northern hemisphere they are anti-clockwise, while anticyclones are clockwise. So how do we get this statement that the cyclones in the northern hemisphere? So you must have seen that the cyclones are shown this way. The in the northern hemisphere, the cyclones, they are shown this way. So let me draw it once. Let me clear this and then show it to you. Right. So if this is the low pressure, so this is how we get this. So the general direction of these cyclones would be anti-clockwise. While for the anticyclones, the same would be clockwise. So the anticyclones, they are shown in another way. If this is the high pressure over here, so they are shown this way. So their movement direction is like the movement of a clock. Now, how do we receive this kind of a movement pattern? So in the previous diagram, as I had shown you, that in the northern hemisphere, if we have the low pressure, the winds are coming in due to the Coriolis effect. We will discuss Coriolis effect in detail in our next lecture. Due to Coriolis effect and the Ferrel's law, in the northern hemisphere, the moving winds will be deflected towards its right, right of the original motion direction. So you can see here, as the winds they are coming in, they get deflected towards right, and therefore we get this kind of a pattern. So if this is the low pressure, and in case of anticyclones, if this is the high pressure over here, winds are coming this way. Oh, sorry. In case of anticyclone, the winds will be going out. Let me draw it. Case of high pressure, the winds are going out, and then these winds will also be deflected towards the right hand side. So this will be deflection direction. As a result, we get this kind of a pattern. So we get a clockwise motion. But remember that this pattern is specifically for the northern hemisphere. In case of southern hemisphere, this pattern changes. In many of the videos and lectures which are on the YouTube or internet, people have just made this statement that the cyclones are anti-clockwise, while the anticyclones are clockwise. But you have to keep in mind that the cyclones are anti-clockwise in the northern hemisphere, and they are uh, clockwise in the southern hemisphere, while the anticyclones they are clockwise in the northern hemisphere but anti-clockwise in the southern hemisphere. So I leave you with this point over here for this lecture. We shall continue on air pressure and the wind belts and how this air pressure belts are varying on the earth in our next lecture. Till then, keep on reading it, and you can join my telegram channel, and you can send me your queries and questions on this email ID. Till then, keep on studying. Bye bye.